Continuity of composite functions. Hello everyone. To begin today's lesson, let's first look back at what we have already covered. In our previous sections, we learned the fundamental methods used to determine if a single, standalone function is continuous. However, as we progress into more advanced mathematics, you will frequently encounter scenarios where functions are nested within other functions. This specific structure is known as a composite function. To put this into mathematical terms, a composite function, written as f circled g of x, is defined as f of g of x in simpler terms. This means the output of the first function, g, becomes the input for the second function, f. Now, the main goal for today is to determine the continuity of these types of functions. The good news is that we do not always need to apply the formal limit definition from scratch, which can be quite tedious. Instead, we can utilize a powerful theorem, which we will explore in the upcoming slides, that allows us to simplify the process by analyzing the inner and outer functions separately. Theorem of continuity for composite functions. Now that we have introduced the concept of composite functions, let's look at the formal theorem that allows us to determine their continuity without having to rely on the complex limit definition every time. First, let's establish our conditions. Suppose we have a function, g, that is continuous at a specific point. See next, we look at the outer function, f. For the entire chain to remain unbroken, function f must be continuous at the point g of c, which is the specific value that function g produces when the input is c. If both of these conditions are satisfied, then the composite function, f circled g of x, which is written as f of g of x, is guaranteed to be continuous at the point x equals c. In short, as long as the inner function is continuous at the starting point and the outer function is continuous at the resulting value, the entire composition remains continuous. In the next slide, we will break this theorem down into a simpler two-step process to make it easier to visualize. Breaking down the theorem. Now, to help you truly grasp the logic behind the theorem we just discussed, let's visualize the composite function as a two-step process. First, we look at step 1, which involves the inner function, g. Imagine the input, x, entering function g if g is continuous at the point c. It means that as x remains close to c, the resulting output, g of x, will also stay close to the value of g of c. Next, we move to step 2, the outer function, f. The output we just obtained from g now serves as the input for function f if f is continuous at that specific value, g of c. Then as the input, g of x, stays close to g of c, the final output, f of g of x, will stay close to f of g of c. Essentially, if both of these links in the chain are continuous, the entire composition is continuous. To make this concept even more intuitive, we will move on to a real-world analogy involving an assembly line in the next slide. Real-world analogy, the assembly line. Now that we have broken down the theorem into a two-step process, let us use a real-world analogy to make this concept more intuitive. Imagine a factory assembly line consisting of two machines. First, we have machine G, which represents our inner function. The role of this machine is to take raw steel as an input and shape it into a gear. Next, we have machine F, which represents our outer function. This machine takes the gear produced by machine G and paints it red. In mathematics, continuity is essentially about stability and predictability. So, if machine G is stable, meaning a small change in the quality of the raw steel results in only a small change in the shape of the gear, we can think of this as the inner function being continuous. Similarly, if machine F is also stable, meaning a small variation in the gear's shape results in only a small variation in the final paint quality, then the outer function is continuous. Therefore, if both links in this chain are stable, the entire production process, from the raw steel to the final painted gear, is stable. This is exactly how the continuity of a composite function works. If the inner function is continuous and the outer function is continuous at the resulting value, the entire composition is continuous. With this conceptual understanding in place, let us move forward to the next slide, where we will discuss the practical, step-by-step process for analyzing more complex functions. Step-by-step analysis of complex functions. Now that we have a conceptual understanding through the assembly line analogy, let's look at how to actually apply this in a mathematical problem. When you are faced with a complex function and need to determine its continuity, I want you to follow these 5 systematic steps. First, identify the inner function, which we call g of x. Simply put, look for the operation that is performed first on the input variable. Second, identify the outer function, f of u. This is the operation that is applied to the result of the inner function, g of x. Third, check the continuity of the inner function, g of x. You need to determine if this first layer is continuous at the specific point you are analyzing. Fourth, check the continuity of the outer function, f of u. Crucially, as we discussed in the theorem, you must check if f is continuous at the specific value that was produced by g of x. Finally, you can reach your conclusion. If both the inner and outer functions are continuous at their respective points, then the entire composite function is continuous. In the next few slides, we will put this step-by-step process into practice with some concrete examples to see exactly how this works in action. Example 1. Analyzing hx equals \sin x $2. Now, let's put the 5-step analysis process we just discussed into practice with our first example. We want to determine if the function h of x, which equals sine of x squared, is continuous for all real numbers. Starting with step 1, we need to identify the inner function. Looking at the expression, the first operation applied to x is squaring it. Therefore, our inner function, g of x, is x squared. Moving to step 2, we identify the outer function. Once we have the result of x squared, we then take the sine of that value. Thus, our outer function, f of u, is sine of u, where u represents the output of our inner function. Now, in step 3, we check the continuity of the inner function. Since g of x equals x squared, which is a polynomial function, we can refer back to our previous lessons where we established that all polynomial functions are continuous for all real numbers. In step 4, we examine the continuity of the outer function. The function f of u equals sine of u is a basic trigonometric function, and as we know, the sine function is continuous for all real numbers. Finally, we reach step 5 for our conclusion. Since both the inner function, x squared, and the outer function, sine of u, are continuous everywhere, we can apply the theorem we studied earlier to conclude that the composite function, sine of x squared, is continuous for all real numbers. This example shows a smooth transition between two well-behaved functions. In the next slide, we will apply this same logic to a more complex function involving absolute values to see if the process remains the same. Example 2. Analyzing hx equals 1x plus x $. Now that we have seen how to handle a trigonometric composite function in the previous example, let us move on to a slightly more complex case involving absolute values. Our objective for this example is to determine if the function h of x, defined as the absolute value of 1 minus x plus the absolute value of x, is continuous for all real numbers. To do this, we will apply the same 5-step analysis we established in the previous slides. First, let us identify the inner function. Looking at the expression, the operation performed first is the part inside the outer absolute value brackets. Therefore, the inner function, which we will call g of x, is 1 minus x plus the absolute value of x. Second, we identify the outer function. The final operation being applied to the result of our inner function is the absolute value. So, we can define the outer function f of u as the absolute value of u, where u is the output of our inner function g of x. Third, we must check the continuity of the inner function, g of x. To do this, we look at its components. We know that the absolute value of x is continuous for all real numbers. Additionally, the expression 1 minus x is a polynomial, and as we have previously established, all polynomial functions are continuous. Since the sum of two continuous functions is itself continuous, we can conclude that g of x is continuous everywhere. Fourth, we check the continuity of the outer function. F of u, the absolute value function, is a well-known continuous function for all real numbers. Finally, we reach our conclusion. Since both the inner function g of x and the outer function f of u are continuous, the entire composite function, the absolute value of 1 minus x plus the absolute value of x, is continuous for all real numbers. While this example demonstrates a successful application of the theorem, it is not always this simple. In the next slide, we will discuss some common mistakes students make when analyzing these functions to ensure you avoid those pitfalls. Common mistakes. Now that we have walked through the step-by-step analysis in our previous examples, it is crucial to discuss some common pitfalls that students often encounter when dealing with the continuity of composite functions. First, let's address the issue of ignoring the outer function's domain. A frequent mistake is focusing solely on the inner function, g of x, and confirming its continuity, while forgetting to verify if the outer function, f, is continuous at the specific value produced by the inner function, which we denote as g of c. Please remember that if the outer function has a discontinuity at the point g of c, the entire composite function will be discontinuous at c, regardless of how smooth the inner function may be. Second, you must be careful not to confuse function composition with multiplication. It is important to distinguish between f of g of x and f of x multiplied by g of x. These are two entirely different mathematical operations. The rules we use to determine the continuity of a product of functions are different from the composition theorem we have studied today, so always identify the operation clearly before applying your analysis. Finally, do not simply assume continuity based on the individual components. Just because function f and function g are continuous on their own does not automatically guarantee that the composite function f of g of x is continuous. This happens if the range of the inner function g results in a value where the outer function f is undefined. Referring back to our assembly line analogy, if the first machine produces a part that the second machine is not designed to handle, the entire process fails. Keeping these common mistakes in mind will help you avoid errors as we move toward our final summary and key takeaways in the next slide. Key takeaways. To wrap up our lesson on the continuity of composite functions, let's go over the key takeaways to ensure you have a solid grasp of the concept. First, let's remind ourselves of the definition. A composite function is essentially a function nested within another, written in the form f of g of x. Now, let's summarize the core continuity rule we have explored throughout this session. For the composite function f of g of x to be continuous at a specific point x equals c, two conditions must be satisfied. First, the inner function g must be continuous at the point c. Second, the outer function f must be continuous at the value resulting from the inner function, which is g of c as we saw in our assembly line analogy. If either of these links in the chain is broken, the entire process fails to be continuous. Finally, let's review the simplification strategy we applied in our examples. When you are faced with a complex-looking function, the best approach is to break it down into a chain of simpler, known continuous functions. By identifying components like polynomials, sine functions, or absolute value functions, which we already know are continuous, you can systematically prove the overall continuity of the entire composition. Keep these points in mind, and you will be able to analyze even the most complex composite functions with confidence.